Rizell from Uppsala University. He's going to be speaking to us about famous work of cocore generating the right Fukaya category.
Thank you, Renato. So it's a pleasure to be here. Thanks to the organizers for inviting me. It's my first time here, and I'm very impressed with many things, mathematics and the beaches and everything. So thanks for that. So I will talk about a result that now is not that new, and my apologies to everyone who's heard this many times before. I'm sure some of you have heard it too many times maybe, but I will try to present it maybe from a different angle. So, of course, I will still kind of necessarily speak about the basics. So first some intro, and then the results, mainly for those who haven't heard this. Then, from a bit new angle, I will try to present this proof as an algorithm that potentially could be used. So I will kind of, instead of giving the proof, I will kind of give an example of how it in practice this result is implemented or conducted. So algorithm by examples. Some very basic examples, but still. And then in the last part, I will try to, if I have time, discuss a bit about some technical points of this. And the main technical input that we needed to use was how to represent cones by geometric objects in the Fukaya category. And that's not possible in general, but we have some special cases when we can do that. I mean, for technical reasons, it's not possible in general as of today, but how we manage to do this cones via Lagrangian surgeries. And this uses Floer homology for some immersions. Sorry for my handwriting. So that's kind of the main technical points of this paper. All right, so some introduction now. Let's start with the basics. So the geometric setup is a Weinstein manifold. Potentially there could be examples where this theory is applicable to, where it's not maybe Weinstein for some reason, but I'm completely unaware of any such examples, and in practice I think it will be difficult to find anything. So I will not bother about that now, but let's just take this Weinstein manifold, which probably is a very restrictive class of exact symplectic manifolds. This is an exact symplectic form. This theta is a part of the data somehow. This is a Morse function. Let's say that it's proper Morse bounded from below finitely many critical points on W. So the Weinstein condition is more or less the following. So I'm not giving the exact definition now, but so the level vector field, let's call it L theta, is a complete pseudo gradient for F. So this is the condition. So basically, the difference between an exact symplectic manifold with some nice boundary, a level domain that is, and this Weinstein manifold is that we have this function F that kind of makes the dynamics of the level vector field completely different from a general level vector field. It becomes like a gradient vector field. And what is the level vector field? If you don't know that, that's defined by contracting the symplectic form gives me this preferred primitive. And what is the use of that? Well, it's important to know that this integrates to a flow called the level flow, and that has the property that it rescales theta. And therefore it also rescales d theta, and therefore it's a conformal symplectomorphism. And even, I don't know, yeah, another consequence of this that is also very important for this talk is that this flow preserves exact Lagrangians. So I think we have seen the definition of Lagrangians some times here, so I will not repeat that. But if it's exact means that this particular choice of theta, it depends on the choice of theta, but an exact Lagrangian is one for which theta pulls back to an exact form. And since this theta is just rescaled by the flow, then of course you can just rescale this primitive of theta. So it preserves the exact Lagrangian condition. Of course, it preserves the Lagrangian condition just from being a conformal symplectomorphism, but this is a really crucial notion here. So this is like, this has nothing to do with the Weinstein part of this story, but that this will be used. Okay, so now the Weinstein structure, this pseudogradient property, implies that this skeleton of W has nice properties. So the skeleton, we take the backwards flow of some very big sub-level set and just take intersections with a negative flow. And this is isotropic. It might be singular, but okay. So that is the main point somehow that we will need. So let me give an example. So the prime example of Weinstein manifold is cotangent bundles. And then in order for this form to be of the type where it's a pseudogradient of the level vector field should be pseudogradient of a Morse function for technical reasons, then I actually have to perturb this, but we don't have to really worry so much about this. So to be strict, just if you haven't seen that thing, then I take the standard level vector field, standard level form, the tautological form on the cotangent bundle. I add some Hamiltonian perturbation to the level vector field by adding this exact form. And then I don't take this bot Morse function, but I take a Morse function on the base somehow. So I kind of, this is not so important, but okay, so the skeleton here is the zero section. And the nice thing here is that it's a smooth Lagrangian, so it's a isotropic, the symplectic form vanishes. That is always the case. Now it is the maximal dimension with that property is Lagrangian, which can be the case. And it's also smooth, which is very atypical. That's only for cotangent bundles. So it's a smooth Lagrangian. Okay, so that's an important example. I will not speak so much about, I will speak about a cotangent bundle and a plumbing of a cotangent bundle. That's all the examples I will deal with today. Any questions about the geometric setup? Otherwise, I continue to talk about what is the aim of the talk. The aim of the talk is to provide some understanding of an invariant of such manifolds. And it's not actually an invariant of the Weinstein manifold, but the underlying level domain. So it's some invariant that depends on W and theta up to, well, symplectomorphism, somehow preserving theta in a bit milder sense. I will not specify it. But this is probably the yeah, it's a very potentially very powerful invariant of a symplectic Weinstein or Weinstein manifold. We don't really know, but it's one of the best things we have gotten so far, at least. So this is the so-called wrapped Fukaya category. So it's this we have heard before, but it's a triangulated A-infinity category. And by definition, it is generated, whatever that means, by exact Lagrangians. So now we need to specify exactly what we mean by this exact condition. So we want them to be embedded for technical reasons, and we want them to be, I will not write that down because that's kind of implicit usually in talks, but they should be properly embedded and cylindrical or invariant under level flow at infinity. So that includes also compact exact Lagrangians. They're also satisfying these conditions. So okay, so we have a category, and by definition, it is something that is generated by some nice subset of geometric objects. And then you have this algebraic machinery. You endow. I will later maybe specify a bit more carefully something about the morphism spaces and so on. But you know, the morphisms between these objects are the wrapped Floer complexes and so on. The main point is now that since we took all the exact Lagrangians, well, that will make it possible to show that this is an invariant of the symplectic manifold, because symplectic morphisms, of course, preserve this set of exact Lagrangians. But it's a very huge class, and we can never understand this class, I would claim. And okay, so maybe we don't, of course, need to take all the exact Lagrangians, but a priori we need to take them kind of, it's enough up to Hamiltonian isotopy, because it's the same as isomorphism in the category. But still, this classification of exact Lagrangian submanifolds up to Hamiltonian isomorphism is still not possible to expect to be able to do in general. So I think this is hopeless. But the point will now be to find a finite set of Lagrangians that actually generate this category instead. So that's the main result. And let me now tell some names about this wrapped Fukaya category. So that is, the technical point is that there are many versions of this, and the first version is due to Abu-Said and Seidel, and then that is done via a homotopy limit, and then there's a version due to Abu-Said himself, which is with the quadratic wrapping, quadratic Hamiltonian. And then there's a new version that is kind of the state-of-the-art technology with these localizations that we heard about yesterday. These some homotopy localizations of infinity categories and so on, which is algebraically much more involved than these previous ones. But it seems to be what people have decided is the correct notion or correct technique. And this is due to this work by, recent work by Ganatra, Pardon, and Schende. So now we have actually three different a priori constructions of this monster here, and all of them with their advantages and disadvantages, maybe. So of course, somehow they're difficult in different ways. But okay, so in the end, we realized that we actually have to take care of, we wanted to prove it in all these settings. So in the end, it's a technical remark, so we have to kind of adapt the proof in these different, well, we consider mainly these two settings, because Ganatra, Pardon, and Schende took care of the theorem in this setting themselves. Okay, so anyway, so this is a technical point, and presumably they are all isomorphic and so on, but it's not clear if it's important to prove that or not, but anyway. Okay, so that's something about the Fukaya category. So again, so the goal is very roughly to find a finite generating set. And we want it to be exact Lagrangians, so geometrically induced. And they will turn out to come from this handle decomposition induced by this Weinstein structure. So there's no canonical handle decomposition, of course, but given a handle decomposition, like this F there, then you get a set of generators. And to understand them, we need to understand how the top, so the critical handles, a consequence is actually that the indexes are less than half-dimensional, less than or equal to half-dimensional here. So the interesting input will come from the top dimensional handles, and we need to understand them. So the critical handle, let me draw a handle. So this is W now. So here we have, this is how a handle looks like. We have a core disk. We have a cocore disk. So this is cocore, this is core. So maybe let me try to use some useful color. So this red is probably visible. So let's, yeah, so these cocores will be important. So maybe let's see, I should, let me try to use blue for the cocores. I'm not sure if that's a good idea. So this red will be something we want to avoid in the end. So let's use, sorry, the core is something that I want to avoid in the end. So let me use red for that. This is something that we will want to displace ourselves from. Okay, so this is the handle, a core and a cocore. And the critical handle, then there is a identification with T star dn. So T star, well, yeah, say T star dn. So this dn is equal to, this disk is the same as the core, that's the C here. And then we have a level form that it doesn't, if I want to do the standard one, then I should not use, I'm not in this bot setting. If I'm in the Morse setting, I will need to Morsify this. But okay, so let me not care about that so much now. Let me just use the standard one. Let me forget about this Morse or bot Morse difference and just let's use this kind of bot handle instead. You can again perturb this. Now maybe it's easier to think about this for you. Okay, so this is how the handle looks like. So observe that the core is just a zero section, which is not a priori any nice Lagrangian inside this category because it has boundary inside the interior of the manifold. So it's not going to it's not proper. However, it is a part of the skeleton, obviously. It is the unstable manifold of this critical point for the negative level flow. So we identified a part of the skeleton here. Then we have D, which is the cocore, and this is actually an object in the category. So now, in a general symplectic manifold, even finding a Lagrangian is a difficult task somehow, it's not anymore true inside a level domain, but it is maybe complicated to find an interesting one. And here at least you have seen the first example of such a Lagrangian, and it turns out that these are actually playing an important role, because that's the generating set. So, okay, so what I want to say more about this? Well, a key point will be that the whole handle is foliated by these cocores, in the sense that I have a lot of different Hamiltonian push-offs here. And these other T star at some other point, they are all isomorphic to D in the category, because they're just Hamiltonian isotopic. I didn't specify exactly what I require from these Hamiltonian isotopies. Of course, there are some wild things that you shouldn't do, but this is a good one. So this will give us isomorphism. Okay, so let me specify that. So these cocores are isomorphic to all of these kind of fibers in there. So let me now recall result due to Ritter that says if there are no critical handles, then this category is trivial. And that, of course, means that whenever I find one presentation without critical handles, then the category is trivial. Then you don't have to worry about it anymore. I mean, you can find, of course, another handle decomposition with handles, maybe very complicated, such a decomposition, but anyway, this category will be not interesting. And the reason is the following very short statement, which can be made precise, but I will not tell you exactly how to prove this. But this is like, since the very early days when in Floer theory by Floer and so on, of course, how can we compute something? Well, usually it's very difficult. Maybe we have some PSS isomorphism telling you that it's just singular homology. And the other case is if it's displaceable, then we can compute it, because then we can actually find a complex without generators, and that complex we know how to compute. This is 0. So the reason is that the skeleton is displaceable, Hamiltonian displaceable, because the skeleton is less than n dimensional. So just by general position, you can displace it. And that is not the case for the critical. If there are critical handles, it's sometimes true still, but this is not so clear. In the cochange bundle, we know that this is not the case, for instance. But this skeleton is displaceable means that actually the generators of any object here can be kind of deformed to 0. And by the way, we already had discussions here in several talks about Roger, and also, I don't remember who else mentioned this, but we had these flexible versions, incarnations of the cochange bundle of an odd sphere, and these embedded in an C odd as a domain. So this is like, for the same reason, here we have an example where the category is trivial. So this embedding is due to Eliashberg and Murphy. And yeah. Yes. Just means that every object is isomorphic to the 0 object. Every identity map in every object in the category is null homologous. So you need to kind of show why. The only thing you need to show is to take any Lagrangian. You don't know what Lagrangians there are there. Consider its endomorphism complex, show that the unit is killed there. So there are many reasons. Maybe you know that, Ritter proved this by saying it's a module over symplectic homology. Symplectic homology is 0 by Kunitz formula. But another reason would be that, well, it's Hamiltonian displaceable, so we have these generators that kind of wrap around the skeleton. They have chords near the skeleton, but I can actually kind of push away my Lagrangian from the skeleton. I can push away the skeleton from itself and miss these generators. So we will see a version of this argument later because it will be important. Yeah, so this, of course, then anticipates this statement that the cocores contain this crucial information. But of course, in this case, this has the homotopy type of S odd, or this odd number here. So this, we cannot get rid of the cocores in this example. But still, due to this displaceability inside C odd, Fukaya category vanishes. So my main point is that here that, well, first of all, cocores or no cocores, this displaceability is one way to compute that something vanishes. And so I think it's, I will soon state the result, but okay. So I will soon say again that, well, here there are potential generators, and from what I'm talking about today, it's not so obvious why this is 0, unless you knew this fact, for instance, that it embeds as a subdomain, as an exact subdomain of, sorry, this is important. Well, okay, it's a sphere, so anyway. So I will not talk so much about how to, one thing is to say that something, one thing is that, I will soon state the result, that it's enough to know what the cocores are doing. Then there's another problem to say, what is a cocore doing then? That is another question, and that's I'm not going to talk so much about. Okay. So now let's talk about the results. So I will just say this then. So this we have proven, and also Renato and Schende has given an independent proof of this. Then of course, there's some different categories there, and it's not clear if you should care about it, but we can get these in all the cases. Yeah. A closed one, yes, but not a. Yeah, so this is the flexible version. So there is actually, that's a proof that there is no exact Lagrangians in this exotic co-channel bundle. So it's not symplectomorphic to the standard one. So of course, then so you cannot, but it's a non-trivial fact that you cannot embed this as an S odd does not embed as a Lagrangian inside C odd. This is a non-trivial fact proven by Gromov in the early days. Okay, so this is generated by the cocores. And then we heard some talks about sectors, Weinstein sectors, and in that we can do it and they can do it as well. So we can upgrade this to sectors as well, and then you have to also include something that I don't remember what term, if Zach, if you mentioned this, you probably said it, the linking disks, maybe, I don't know if you said the word. Linking disks, or spreadings, as we call them, of cocores of the stop. Anyway, there are some natural cocores near these stops in the sense of Zach here. Let me not go into this. Okay, so what else is important here? if you combine these results with all the results by Ganatra and recent results by Gao, then you get the Abu-Zaid generation criterion holds, which somehow is implies a weaker statement, namely that these cocore split generate. But it's still useful because this generation criterion is in terms of a computation of a map called the open-closed map. And knowing that can give you other generation criterions. For instance, if our proof, I would say these two proofs do not say anything about, a priori at least, non-exact Lagrangians. So it could be that when you want to extend this category, which some people already did, to include some non-exact Lagrangians, like monotone ones, then we don't say anything about that. We don't say that our Lagrangians, or sorry, the cocores generate these ones. But then this generation criterion could say that at least it split generates, for instance, in some cases. So this is a technical point that for the ones who are experts, I suppose. And also this also gives you that symplectic homology is the same as Hochschild homology of this category. So let me just say that. Yep. So. No, I don't think I know that. But I didn't look for one either, so that I don't know. It is clear that the proof fails, but I mean, maybe they are generated somehow by the, say, in some cases, by the skeleton. If you take compact ones, at least, maybe there's a smooth, maybe it's cochrane bundle, and they're kind of generated by the zero section in some way, and the zero section is generated by the cocore. So maybe it's difficult to find such an example, but I don't know. Question there? Yeah, so there are algebraic examples now that we know. I can't give anything explicitly, but we can. So any W. So maybe we heard about this already. No, maybe not. So Oleg Lazarev has shown that this is equal to some flexible union of handle. So somehow here. You can prove that this handle split generates, sorry, the cocore of this handle split generates the whole thing. But in fact, it does not generate, because some Fukaya categories have more than one generator necessarily by K-theory. So this is a geometric, I cannot see it here, but say K-theory is a reason. That's one obstruction at least. So this is one point. So our theorem is not a surgery formula, for instance. This would follow by some kind of more surgery formula. If you have this one, here's a vanishing wrapped Fukaya category. I attach something, and then I explain the whole thing by just what I attach. This can be done, but you need some input from either this old work by Bourgeois, Coleman, Eliashberg, or GPS, for instance, and about how to glue categories. And this is not something that we're doing here. But using such theories, either GPS or Bourgeois, Ekholm, Eliashberg, you can kind of get surgery formulas here and explain what the difference is here. And for instance, this cocore split generates. But this is not something that we're doing here today. And something else that we're not doing is we're also not computing so the endomorphisms of D is a cocore, or let's say hom DD, which is by definition a wrapped Floer complex of D and D. this I will not. This theorem doesn't care about that at all. It's taking this object, whatever it is, geometrically and producing some morphisms. And for what you might know, all of these morphisms might be zero. But what I will do for you is, in any case, I will take L, an arbitrary exact Lagrangian, and the proof here of this theorem consists of saying that L is isomorphic to some iterated cone of such cocores. Yes, so this is what we want to say, that taking a bunch of these cocores and then wrapping them a bit, resolving double points, and so on. That will lead to, so L is embedded by assumption. This kind of geometric incarnation of these cones, we claim that it is this embedding here, but it's also more naturally built up from these embedded disks by some kind of surgery, which then is not embedded, but exact, in fact. So that we will see soon. But still, so this is what we do. So this is our work. And we can do this, and our method, observe that our method doesn't really care whether we're in this case, the flexible one, or the standard one. So we will see how to do this, build this cone, but it might be, this thing here might be zero for all you might know. Just to clarify a bit what we're doing here. So then if you actually want to compute these spaces, which is crucial, then you need some other theory, again, to compute it in some local models and then use GPS or use the surgery presentation by Bourgeois, Ecolmel, Jarsberg. So very quickly now, the strategy. How to do this. Strategy for this. How to construct this. Well, to construct, construct this, the cone of, by definition we can always take cones because we're in this triangulated version of the Fukaya category. So if I have a morphism here, first I want to construct an isomorphism, but first I construct a morphism. So I want to construct a cone of that morphism. So I take L, and I hope to be able to construct a cone at least from L to some other cone then, iterated cone of these cocores. Let me just draw it like this. Okay. So in the end, if I first I have to construct this cone. That on its own it's not completely trivial because I have to solve the generalized Maurer-Cartan equation, which involves these infinite operations. So let's see here. So I have to, So if I call these CK, these morphisms here, then basically it's A plus C1 plus etc. A plus this is a bit messy. I have to show that these morphisms, if there really are morphisms, this should satisfy this Maurer-Cartan equation. So I have to, roughly speaking, take their sum and if I apply the infinite operations with the insertions, this morphism, this endomorphism, kind of the total, the sum of all these objects, then it should be 0. Anyway, there's an equation there that needs to be satisfied. If that can be found, then at least I can build this cone. So this I need to solve. Then, so this is somehow first step. Then I need to show that this A is an isomorphism. And even if I get this structure, of course, I can take these to be the zero morphisms or whatever. I need to know why this A is an isomorphism. So A is a quasi-isomorphism if and only if above cone is acyclic. And this cone is acyclic will be shown by represent cone by exact immersion inside W minus a skeleton. So the hope is to find some algebraic object here in the category which has a geometric representation by an exact immersion away from the skeleton. And then we will use this ancient idea of displacement to show that this cone, this cone a priori has no geometric embedded representative in the category. L has, DI has, but this cone might not have. We claim that we can construct now an immersed representation, an immersed representative, exact immersed representative. And if we construct this morphism in the correct way, then this representative is moreover in the disjoint from the skeleton. Yeah, but then all the Ritter's results said that we don't have to do anything, luckily. So we're saved by Ritter in that case. So the theorem is now that, or maybe it's not a theorem, maybe it's a proposition, an immersed exact, so this immersion, let's call it L, some fat L in this hash, because it will be obtained by some Lagrangian surgeries. And any here, well, unobstructed is necessary. Inside the complement of the skeleton satisfies is the zero object in a certain sense, namely if I take another test Lagrangian and then compute the Rapp-Fleur homology of this test Lagrangian and this other Lagrangian that is disjoint from the skeleton, then I get nothing, in homology. Yep.
Is L sharp representing the iterated cone or the cone of
Sorry, so this whole thing. So this is L sharp should represent this whole thing. So I have an object in the category. I want to show that this is the zero object. That means that A is an isomorphism. And the way to do that is to find a geometric representative that is disjoint from the skeleton, and then this theorem proves it. And the proof is displacement. And somehow, let me draw this picture. So, I don't know if you can see this, but the complement of the skeleton is the symplectization. And translation here is the level flow. So the level flow preserved exactness. That was the crucial property. This t direction here in the symplectization is just a level flow. That's how the complement of the skeleton looks. If I have t here my Lagrangian, I want to wrap t, which means that I have to start to go around here. Wrap T. So I have many generators here. Generators. But I can find a Hamiltonian isotopy to a complex. Sorry, this was the wrapped version. I just push it up. Oop. I just push it up with the level flow. That is somehow generated by a Hamiltonian, meaning that the Floer complexes are invariant. So these generators that I see here, so this chord conjecture that we heard about tells me that probably I can never really hope to, well, if I wrap above here, I will always see chords probably, I will always see generators probably, but in the complex they will not contribute because I can just shift away. This can just sneak up here and nothing will be seen. So even if I see generators, they are null homologous. So this is the proof. So in the non-exact case, this has been shown by other people, like Abozaid Seidel and Chilbach-Wonsha are examples that I know. Okay. So I think I will not have time to talk so much about the immersed Floer theory. So let me now go on to do some examples of the algorithm. So the rule is so we want to solve the Markov equation by, I mean, first of all, we want to construct such a cone, or sorry, the morphisms A and C, I. We need to solve the Markov equation, but we also need to somehow be able to resolve these A's so that we get disjoint from the skeleton. So now, this kind of rule that we will use is that if I see the skeleton somewhere, and then if I see the Lagrangian, a Lagrangian here that touches it, then I want to put D here. So let's say L here. Then I want to put another Lagrangian there, namely the cocore, and I want to resolve it. Oops, so A here. So this red is the skeleton. And A is a double point, but I can interpret it as a morphism from D to L or from L to D. But if I interpret it now, I say it's a morphism from L to D, sorry. Kind of, that means that, some rule about this corner here, then the cone of this A should be given by this connect sum. So there are two different such resolutions. Sorry, this is the Lagrangian surgery. So there are these two different. We can resolve the other way, but when I consider this morphism from L to D, I do this kind of resolution. Yeah, so now this is actually not the complete. So now it's just a guideline. And I probably do not have time to show you why this is actually. So let me just say it, that of course, in order for this to work, when there are other intersection points, we have to be very careful. And that, I promise you that we are very careful. But the carefulness comes, mostly is about showing that when you do this, that you still get an exact Lagrangian. That's actually the technical point that we need to ensure. Yeah, so this will be kind of L sharp. So let's in some very basic cases, this is exactly that. Say I have a Lagrangian intersecting the skeleton in one point, then I do exactly this, and I get the statement. So in some very cases, this is actually proof if there's a single intersection point. Otherwise, there's a mess. So now let me try to give you the algorithm. And I will do a Lefschetz vibration picture. So locally, I have this Z is quadratic Lefschetz singularity. And then I will say that this picture looks like, here I have the skeleton, and the picture that I want to see is that I have D here and L here. So this is the origin, the critical point. So these are Lefschetz thimbles now. So I think we have seen these pictures before. So I want to smoothen it here. So A is here. So I will draw these pictures. So this first step Hamiltonian perturbation, Hamiltonian perturb L, so that L intersected with the skeleton is inside the union of the cores. So first of all, it should be transverse to the skeleton. It thus consists of a finite number of points. And these points should moreover be contained inside the union of cores. Let me write it like that. So there are lower dimensional strata, but of course L is n-dimensional, so it will generically not intersect this lower dimensional strata. So we just intersect the cores. That's the first step. This is very easy. Then place a cocore. We had this whole foliation by cocores. So these kind of blue things at each AI. And now use this kind of rule, have this rule in mind, that I want to place them so that when I resolve it, I disjoin from the skeleton. So I will now draw T star Sn, since that is something that has occurred in many talks here. So T star Sn. I have, say, okay, well, what is L? L is just a copy of the zero section. I perturb it a bit. Of course, there's a single cocore here for some nice handle representation. But I have two intersection points, A1, A2. I put a cocore here. So let me draw that in blue, maybe. It was my convention. I will probably fail. So D2, D1. So in fact now, D1 is obviously isomorphic to D2 because there's a single critical handle, but never mind. We need to put these geometrically in different positions so that they kind of live above the double points. But we want to follow the rule, and the rule does not apply to that picture because this picture is not according to the rule, because you see here's DL. This is okay. If I resolve it, I get away from the skeleton. But here, if I resolve it in the same way, I go around here. I do not resolve the skeleton. So I need to deform this picture. So according to rule, which means that I have the following. I mean, this is very easy. I just do this instead. Now I'm in a situation where I would like to say that if I take this, resolve it according to the rule, then I get this thing that is an immersed curve, immersed cylinder upstairs is disjoint. However, one problem is that I needed also to solve the Maurer-Cartan equation, and that I cannot do here. So this is obstructed and here A1, and here I have something, let's call this D. So mu 1 of A1 is equal to D. This does not solve the Markov-Cartan equation. So this was the wrong thing. So I have to actually do another step. Wrap with negative rib flow. And that I do not make precise here because you have to be a bit careful here so that the action works in your favor. But in this case, what the algorithm would tell you, I'm not telling you the precise algorithm, but what I would do is I will just wrap D1. And I will wrap D1 like this. This is the negative wrap of D1. And actually I do not want to wrap D2, I want to keep D2. And naturally I would have to wrap D2 as well, but I will not go into those things now. So this is D1, this is L, like that. So this is the D1 wrapped. This is D2. Yes. So this is the negative wrapping of D1. And now I have some intersection points here, A1, A2, B, C. Okay, I have some more upstairs there, but let's not discuss that. And again, A1 plus A2 does not solve the Markov-Cartan equation, but A1 plus C solves. And that's due to this triangle here. And this triangle here tells you that mu2 of A2 C is equal to B. And here, this one here says that mu1 of A1 is equal to B. And due to this triangle, we can actually solve it, because we can, if mu of A1 spits out a B, yes it does, then I can add a C here, and suddenly the Markov-Cartan equation is solved. And what does this tell you? So I'm running out of time here. So this tells us that the cone is represented by this thing here. Is disjoint from the skeleton, so this is isomorphic to 0. And more precisely, it tells you that L is, this A is an isomorphism. And it's quasi-isomorphic to the complex being the cone of D2 to D1. So it's a cone of an endomorphism of the cocore. So do I have like 1 or 2 minutes or something like that? I don't remember. So that was the first example. I can do the same thing. I can do exactly, or more or less exactly the same picture, provides a cone decomposition also for the flexible case. However, it will not give anything interesting because the endomorphism ring of the cocore is 0 in that case. So I'm just pointing out here that I'm providing a cone decomposition, but it might give us nothing interesting. In this case, there is an embedded Lagrangian there, so we know it's not a trivial statement. Okay, you can say maybe C is zeromorphism. This I didn't argue for either, but this I think you can do by grading reasons. Okay, so let me just finish by a very quick alternative computation of a result by Abu Zaid and Smith, who argues very similarly, but they had to mess around a bit with other things, a bit ad hoc, geometrically ad hoc, because they didn't have this immersed Floer homology to deal with this kind of object here. So this is unobstructed, and that's what we use. So they use an alternative way. So they basically want to, now they do the plumbing. So here we have a sphere, here we have another sphere. So plumbing to T star S ends. Then we have generally two cocores, and they're not isomorphic. Colors, I'm not good at this. And this is also D2, D1. D2 is not isomorphic to D1 in this case. Let's take L to be kind of another cocore, but now which intersects both of them. So what is L then? Well, L is equal to, again, cone by something that is a morphism from, it should be same, some morphism from D2 to D1. And again, so you let me not go into, let me leave this as an exercise. I will just give you this picture. This is the one-dimensional case, but okay, so here we have L. Here I have the skeleton, and I want to, so here I have to put one cocore. That looks according to the rule, because if I resolve this, get a morphism from L to the cocore, then it is disjoins. Here I have to put it in a bit, so blue has to go on this side, so here I have to kind of sneak it in like this. And then I have to actually wrap this over here and get the same result. So that finishes that computation, and okay, my time is up, so thank you for listening.